We've alluded to the r hat vector a couple of times in previous videos here, and where its position is most commonly seen is in Coulombs Law. The force here is k q1 q2 over r squared, and this portion of the equation here describes the strength of the force between two charges, one of amount q1, one of the amount q2, given that they're a distance r away. That gives the strength of the force, and the r hat sits here and discusses or talks about the direction that force would act in. And so you have a magnitude and direction, as you should, because a force is a vector. The other time we've seen the r hat is also in the electric field equation. The electric field looks very much like the force equation, but they're different. It's still the same constant. There's only one charge now, and we made a special case here to say, well, it's the source charge, because it's the source that sits here and fills all the space around it with an electric field. And in case of the positive charge, the electric field lines, of course, would point away from it. So this is the source charge right here. So this portion of the electric field equation describes the magnitude of the electric field. And the r hat sits here, once again, like in the force equation, describing the direction. So what I'd like to do in this video is just give you a good rundown of what exactly r hat means, because it's perennially confusing to students. So we'll just do it as an example here to say, hey, here's what the r hat vector means, and here's how it works. What I'm discussing might be a little advanced, particularly if you're in an introductory physics class studying electricity, but nevertheless, this is how r hat works. Here we go. So what we'll do, we're going to start out with an example like this. Let's say there's a Cartesian coordinate system like this, and there's a negative charge sitting here, and up here is a positive charge. And there's a line, of course, that connects them. This is the r that connects the two charges here, and let's just say that this distance here is 2 centimeters. So two charges are 2 centimeters apart. Let's just say this is a minus 5 nanocoulomb charge, and this one up here is a 10 nanocoulomb charge, just to get some numbers out there. And to really just sort of mix things up, we'll say that this angle that the charges make relative to the x-axis over here is just some weird number like 53 degrees. This is the x-axis and this is the y-axis. This is sort of set up for the problem. So I just have a bunch of numbers in there, and using this problem here, we'll see if we can nail down just what is r hat. What does it mean and how is it used here? Okay? So here's what we'll do. The first thing we can do is just calculate the magnitude of the forces between these two charges. That's pretty straightforward here. I'll just write F with no vector sign in here. That's just going to be the constant times 5 times 10 to the minus 9. That's the amount of charge on this one here. And I'm dropping the minus sign because, as I showed you in some other videos, I like to sort of think about these as like absolute values. So I'm just going to drop the sign. I'll assign the direction with common sense in just a second. And over here will be the 10 nanocoulombs. 10 times 10 to the minus 9 coulombs, like that. And of course I divide by r squared, which is 2 centimeters converted to meters, 0.02, that quantity squared. If I plug all these numbers in, I'll get the magnitude of the force, which comes out to be something like 1.13 times 10 to the minus 3 newtons. Okay, this is the magnitude of the force that exists between these two charges here. But the problem is far from complete because we haven't determined the direction that the force acts relative to the two charges. So what I'll do now is I'm going to drop up to my common sense, which I've sort of alluded to in some other videos also, and I'm just going to label the direction of the force in here. Like, for instance, I know the negative and positive charges attract each other, so I know that the force on the negative charge, because of the positive charge, is going to point up like that. And I know that the force, because of the negative charge on the positive charge, will point downwards like this. Like, those are some things I know. That's my common sense. But that's about all I can do at this point. I can't really nail down this direction any more specifically than that, because now I need to work on the r hat. Okay, so here's the way the r hat's going to work. Let's just form, before we do the r hat vector, let's form the r vector. And the r vector will be the full vector that connects these two charges given this 2 centimeter distance. So r hat then, if you look at it then, or r vector rather, if you look at it then, comes from a right triangle here like this. So here's a right triangle like this. There's the hypotenuse right there. And this angle in here, as I mentioned, this angle right in here is your 53 degrees. So given that, we just fall back on using x, y vector components the way you did maybe in another physics or math class here. This side right here, because it's the adjacent side to the angle involved the cosine, will be 2 times the cosine of 53. This side over here will be 2 times the sine of 53. That's how we can get the magnitude of these two sides. And if we put that into the calculator, that's going to be in this side right here. It's going to be a length of 1.2 centimeters, and the side up here is going to be 1.59 centimeters. So that's just the way this triangle works. Given that there's a 2 centimeter distance at an angle of 53 degrees relative to the x-axis, this side is going to measure 1.2 centimeters, and this side is going to measure 1.59 centimeters. That's just sort of basic trigonometry. But why I want to do that is because with those two numbers now, we can form what the r vector is going to be. In fact, the r vector is going to be 1.2 centimeters along the x-hat or x-axis plus 1.59 centimeters along the y-hat axis or y-axis. This is the r vector. Now, to get the r-hat vector, the reason why it's called r-hat now is because it's like the r vector, but its length has been normalized to be 1. In other words, the magnitude of the r-hat vector, any vector with a hat over, is always equal to 1. The magnitude of the r vector is not just 1. In fact, if we took the magnitude of the r vector, we could do it real quick in our heads, Pythagorean theorem, 1.2 squared plus 1.59 squared, and take the square root of it, but we know we'll get 2 because that was the original length of the vector in there. So the magnitude of r vector is 2. The magnitude of r hat should be 1. So how do we get r hat from r? Well, all we do is we just take that r vector like that and divide it by its magnitude like that. So if you take a vector and divide it by its magnitude, you will get just 1. So let's just proceed to do that then. So what this will come out to be then is the r hat vector would just be 1.2 x hat plus 1.59 y hat over the magnitude, which is 2. So we're going to divide each component by 2. So the r hat vector then will come out to be 0.6 x hat plus 0.795 y hat. So this is that elusive r hat vector. It gives everyone so much trouble when it's tacked on the electric field and the Coulombs Law equations here. And we're not going to check here, but if we check the magnitude of r hat here, we should get 1. In other words, 0.6 squared plus 0.795 squared, square rooted, should give 1. So we have the r hat vector. So what this means then for us is that we just redraw the figure down here. So we have a charge down here. This is our original scenario here. We have a negative charge right here and a positive charge over here. And we have this line connecting them. And up here we sort of empirically drew the direction of the forces, downwards and to the right for the positive charge, downwards and to the left for the positive charge, upwards and to the right for the negative charge, but that's all we could do. But now we can get in and very specifically specify what that direction is using this r hat vector. In fact, what we know about r hat is that both of these directions have 0.6 units along the x-axis and 0.795 along the y-axis. So if you kind of wanted to draw that, it would look something like this. 0.6 is a little smaller than 0.7, so I'll just try and draw it. We have an r hat vector, so it looks like this. That might be 0.6. And I'll draw another arrow, which is just a bit longer like this to indicate the 0.7. But this is sort of the angle or whatever that would be indicative of the r hat vector. So that's sort of what this tells us. This is how the forces point. They always have 0.6, an extent of 0.6 along x hat and an extent of 0.795 along y hat. But let's just sync that up a little bit better now and just see if we can write the full Coulombs Law then. Because we know the magnitude of the force. We calculate that up here was 1.13 times 10 to the minus 3 newtons here. But if you want the full vector force now, what you would do, so here's the force with the vector of it, you would use that magnitude up there. We'll pull that number down in just a second. We use this number here, but now we just multiply by the r hat. And this is because, remember, f vector is k q1 q2 over r squared times r hat. Remember, that still holds. So all we have to do then is to get the net force vector is just multiply the 1.13 times 10 to the minus 3 newtons, and we'll just multiply that by the r hat vector, 0.6 x hat plus 0.795 y hat. Just multiply it like that. And what we'll get when we're done, we get a force vector then, which is 6.8 times 10 to the minus 4 x hat plus 9 times 10 to the minus 4 y hat. And of course the whole thing is in newtons here. So this is our result. That shows you how that r hat vector is used then. We have the full vector Coulombs Law result for the force between the two charges. We have the amount that the force tugs on either charge in the x direction. We have the amount the force pulls in the y direction. If we want to know the total force, remember we still have that up here. That's the 1.13 times 10 to the minus 3. We'd still have that, but now we have, given that the r hat is wrapped into it, exactly how much the pull is in the x and or y direction. And of course the angle between this component and that component would give 53 degrees. Nothing's going to change there. But this is a very precise and exact form of exactly what that force is going to be, including the components and the direction. So that's how the r hat vector works. And just remember that the key step here is this is probably easy for you right here. This is the vector length between the two charges, but dividing a vector by its magnitude is what gives r hat. This gives a raw normalized direction vector, in this case the 0.6 and the 0.795, telling you the direction, the very specific direction between the two charges. And if you multiply that by the force, then you can get the Coulombs Law in all its glory there. That's how r hat works.